Welcome back to our STL journey. Today marks day 15 and we are diving into an essential part of the STL, the set container. Sets are perfect when your goal is to manage collections of unique values and you want either fast access or sorted ordering. Throughout today's session, we will explore the two major variants, the ordered set and the unordered set. You will learn how they work, when to use which, and how to apply them in practical programming situations. By the end of this lesson, you will have a clear understanding of how both set and unordered set work. We will cover syntax, internal implementations, operations like insertion, deletion, and searching, and the performance characteristics that differentiate them. You will also write some code, analyze time complexities, and try out coding exercises that simulate real world use cases. The goal is to help you make an informed decision about which type of set to use depending on your needs. A set in STL is a container that stores only unique elements. That's the key idea. If you try to insert a duplicate, it will be silently rejected. The main use of a set is when you want to filter out duplicates, search efficiently, or maintain a sorted structure. There are two kinds, the ordered set, which automatically keeps its elements in sorted order using a red flag tree, and the unordered set, which uses a hash table and provides constant time average access. We will be focusing on both in this session. Let's start with set, the ordered version. This is implemented internally as a red flag tree, a type of self-balancing binary tree. That means elements are always kept in sorted order and all operations insert, erase, and search run in log n time. You can think of set as a sorted list that does not allow duplicates and allows fast lookup. It's best when ordering matters, like when building a leaderboard or sorting a set of names automatically. Here we see some operations for std::: set. First, we declare a set of integers. When inserting values, any duplicates are silently ignored. Try inserting 10 twice and you will see it only appears once. Searching is done using the find function, which returns an iterator. If it matches the end iterator, the element wasn't found. Deleting is as simple as passing the value to the erase function. All of these operations are fast and reliable, and due to the tree structure, elements are automatically ordered. Now let's shift our focus to unordered sets. This container has the same property of uniqueness, but it's not ordered. Internally, it uses a hash table, which gives us average case of week of 1 performance for insertions, deletions, and lookups. However, since it uses hashing, the elements do not maintain any specific order. It's great when you care about speed and not about ordering. For example, checking if a user has already logged in or if a word has already been processed in a large text. In this example, we create an unordered set of strings and insert several values, including a duplicate. Notice how Apple only appears once. We can use find to search for specific entries. The lack of order might look odd at first, but the performance gains are significant. This makes unordered set an ideal choice when you are dealing with large data and just need fast, reliable lookups like checking if a number has already appeared in a string. This table helps summarize the core differences. In terms of internal structure, set uses a balanced tree while unordered set uses a hash table. That means set provides log n time complexity and unordered set gives constant on average. The trade-off is that set maintains order while unordered set does not. Use set when order matters or when you need predictable traversal. Use unordered set when you just care about speed and don't need ordering. Both reject duplicates, but the underlying behavior is quite different. When should you use sets in real applications? Use set for leaderboards, ranking systems, event timelines, or anywhere you need sorted unique elements. On the other hand, use unordered set for fast filtering, checking presence of elements, or removing duplicates from large datasets. For instance, if you are analyzing user activity logs and want to know how many unique users visited a page, unordered set is the way to go. Here's a quick practical task. Suppose you have a vector with repeated integers. How do you remove duplicates? Simply pass the vector elements into a set using an iterator range. This instantly filters out all duplicates. If you care about performance, use unordered set. If you want the results in sorted order, go for set. You can even convert the set back to a vector if you need array style access later. This next exercise simulates a real-world use case, text analytics. Given a paragraph of text, you want to count the number of unique words. Step 1. Break the text into words using a string stream. Insert each word into an unordered set. Return the size of the set. This simple pattern powers everything from spam filters to keyword extractors. Just try it out. Let's run a quick performance comparison. We generate a large list of random numbers and measure the time taken to insert and search in both set and unordered set. You will usually find that unordered set is significantly faster, except in rare cases where hash collisions degrade its performance. Meanwhile, set offers more consistent behavior and predictable iteration. These benchmarks help you decide which container to use based on context. Here are some key tips. First, once an element is inserted into a set, you cannot modify it directly, because doing so might break the internal ordering or hashing. You will need to remove and reinsert. Second, if you use custom data types in an unordered set, you must define a custom hashed function. Lastly, don't assume one is always better than the other. Profile and choose based on your application's need. Time to get hands-on. Here are some practice problems for you. Remove duplicates from an array using a set. Count distinct elements in multiple arrays. Check if two strings have the same set of characters. Find the intersection of two arrays using sets. These problems will give you strong muscle memory with set containers. Try them on LeetCode, HackerRank, or Codeforces. On day 16, we are going to level up. We will look at multisets which allow duplicate values. They are great when you want to count the frequency of elements while keeping them sorted. We will also compare them to sets and see where each fits best. See you in the next session where we go one level deeper in mastering STL containers. Welcome to day 16 of our journey through the C++ standard template library. Today we explore a very interesting and often underutilized container, the multiset. Unlike the set container, which strictly disallows duplicate values, a multiset permits duplicates, making it ideal for cases where repeated values are significant. Just like set, all elements remain sorted by default in ascending order, and this property is maintained internally using a red-back tree, which is a type of self-balancing binary tree. This structure ensures that operations like insertion, deletion, and search are always efficient regardless of the number of elements. A multiset is categorized as an associative container in the STL. The term associative means that elements are sorted and accessed based on their values rather than positions or indices. What makes a multiset unique is its ability to store duplicate values. Multiple elements with the same value can coexist. Additionally, the container automatically maintains a sorted order, so you never have to manually sort the data after inserting elements. The internal mechanisms of the multiset are designed to offer fast access for searching, inserting, and deleting elements, all with a time complexity of log n due to the underlying balanced tree. Creating a multiset in C++ is very straightforward and feels just like declaring a regular set. For instance, you can write multiset int ms to create a multiset of integers, or std::: multiset std:: string names for sorting strings. This container is highly versatile. It supports user-defined types as well, provided you define how elements should be compared, usually through overloading the comparison operator or by passing a comparator. This makes multiset a powerful option in real-world coding scenarios where duplicates and sorting matters. Inserting values into a multiset is similar to other STL containers. You simply call the insert function. Here the key point. Unlike set, the multiset allows you to insert the same value multiple times. In this example, 10 is inserted twice, and that's completely valid. Internally, the red-black tree structure adjusts itself to ensure that the values remain sorted after each insertion. So no matter how many duplicates you add, the order is always preserved automatically. Now let's talk about deleting elements from a multiset. If you use ms.erase10, it will remove all instances of the value 10 from the container. So be careful when using this. But what if you want to remove only one occurrence of a value that appears multiple times? For that, you can use an iterator. First use find to locate the value and then pass the iterator to erase. This approach gives you fine-grained control over the deletion process, which is crucial when working with repeated values. The multiset offers handy functions like count and find to work with its contents. The count function tells you how many times a particular value appears in the multiset. This is especially useful when you are analyzing frequencies or validating duplicates. The find function returns an iterator for the first occurrence of a given value. If the value does not exist, it returns ms.end. This is particularly useful when you are looking to perform operations on specific entries. Iterating through a multiset is both simple and powerful. Using a range-based for loop, you can visit each element in sorted order, and yes, that includes duplicates. So if you have inserted the number 10 3 times, you will see it 3 times during iteration, appearing in their proper sorted position. This property makes the multiset ideal for outputting or analyzing ordered data with repetitions such as logs, scores, or events. By default, multiset sorts elements in ascending order, but what if you need the largest elements first? That's where custom comparators come in. By passing greater in as the second template argument, you can create a multiset that sorts elements in descending order. This is extremely useful in applications like leaderboards, priority systems, or anywhere you need to track and display the top values first. Let's compare set and multiset side by side. First and foremost, sets do not allow duplicates while multisets do. In terms of performance, both offer logarithmic time for insertion and lookup due to their tree-based structures, and both maintain sorted order. So the main deciding factor is whether your use case requires duplicate handling. If yes, multiset is the clear winner. Let's explore where multisets shine in real-world applications. You can use them to store game or exam scores where multiple players might have the same score. They are excellent for word frequency analysis, where each word's occurrence is counted. They help manage timestamps and event collisions, particularly in logging systems. And finally, they are useful in frequency counters when you want to build one quickly without using a hash map. Let's look at the internal complexity of multi-set operations. Insertion, deletion, and search all have a time complexity of log n thanks to the self-balancing red-black tree. Iterating through the multiset takes n time since you are simply walking through each element in sorted order. This consistent performance, regardless of data size, is a major strength of tree-based containers like multiset. Let's bring it all together with a quick hands-on example. First, take a list of numbers from user input or a file. Insert these numbers into a multiset and remember, duplicates are welcome. Next, use count to find how many times a value appears. Finally, practice erasing both all occurrences of a value and just a single instance. This hands-on session will solidify your understanding of multiset behavior. There's a practical use case, an exam score tracker. Students often take multiple tests and we need to store all their scores. A multiset is perfect for this because it allows repeated scores while keeping them sorted. You can easily retrieve the top few scores using a descending multiset or remove a specific score if a re-evaluation occurs. It's clean, efficient, and gets the job done without extra logic. Let's summarize today's key points. The multiset container allows you to store duplicate elements while maintaining them in sorted order. It is built on Blackbird tree, which guarantees logarithmic time complexity for core operations. Insertion, deletion, and search are straightforward, and you can use custom comparators to tweak the ordering. All of these features make multiset an ideal choice for applications that are sensitive to duplicates and order. To reinforce today's learning, here are a few practice problems. First, try inserting values with duplicates into a multiset and use count to track how many times each appears. Next, implement logic to erase only one instance of a duplicate value. Finally, use a descending multiset to store a list of scores and retrieve the top 3 highest values. These problems will help you gain practical mastery of the multiset container. Welcome to day 17 of our journey into the standard template library. Today we are focusing on one of the most powerful and widely used containers, the map. Whether it's an ordered map or an unordered map, this data structure forms the backbone of many real-world applications like indexing, counting, and searching efficiently. We will also explore how key-value pairs work using pair and see how maps give us flexibility and speed in storing and retrieving data. Let's dive in. A map in STL is an associative container that stores elements in key-value pairs. Each key must be unique and it maps to exactly one value. There are two main types: an ordered map, simply called map, which maintains its elements in sorted order by key; an unordered map, which uses hashing for fast lookups and does not maintain any specific order. Internally, map is implemented using a red tree, giving us logarithmic or log n time complexity for insertions, deletions, and searches. On the other hand, unordered map uses a hash table, giving us average constant time for the same operations. However, in worst case scenarios like hash collisions, it can degrade to n. This makes understanding the internal implementation important when choosing between the two. Let's look at how to declare maps. We can declare an ordered map like std::: map int, string, id to name. Here each integer key maps to a string value, perhaps an id mapped to a person's name. For faster access, we use std::: unordered map string, int, word count. This would be great for counting word occurrences. Remember, map keeps keys sorted while unordered offers no guaranteed order. Make sure to include the correct headers: map for ordered maps and unordered map for unordered ones. There are multiple ways to insert data into a map. The simplest way is using the subscript operator, m key assigned value. If key does not exist, this creates a new entry. If it does, it updates the existing value. You can also insert using m.insert key, value, or even better, use mplace for efficiency. m.mplace key, value. Why is mplace better? Because it constructs the pair in place, avoiding a copy or more. A key point to remember: maps don't allow duplicate keys. Inserting the same key again will override the existing value. When you access elements using the subscript operator like this, mKey, you need to be careful. If the key isn't present, the map will automatically insert it with a default value. That's not always what you want, especially if you are just checking for existence. A safer way is to use m.addKey. This throws an exception if the key isn't found, avoiding unintended insertions. The most robust approach, use find. This allows you to check if a key exists before using it. You can traverse a map using a range-based for loop or iterators. Each element in a map is a pair where dot first refers to the key and dot second refers to the value. Here P is a reference to each pair const key, value. You can also destructure the pair directly. This makes your code cleaner and more readable. Here's a side-by-side comparison of map and unordered map. Use map when you need keys sorted or want predictable traversal order. Use unordered map for placing fast insertions and lookups, provided your keys are hashable and you don't care about order. Each element in the map is essentially a pair const key comma value. Understanding how pairs work is essential for using maps effectively. You access the components with dot first and dot second. Using structured bindings makes it even easier. This way, your loop variables directly hold the key and value, making code more readable and concise. Maps are mutable. You can modify their contents easily. To remove an element by key, use m.erase key. To clear all element, use m.clear. To check for existence without inserting, use m.find key. It returns an iterator to the key if found, or m.end if not. Let's walk through a real-world example counting word frequency. Here each word is read from input and its count is incremented. Why unordered map this time? Because it gives us constant time insertions and lookups, making it perfect for counting, indexing, and grouping data efficiently. There are a few common pitfalls when working with maps. Using M key on a missing key inserts it, sometimes unintentionally. Unordered map does not work well with custom classes or complex types unless you provide a hash function. Iteration order in unordered map is not guaranteed, so never rely on it for ordered output. Be mindful of these quirks when choosing and using map containers. Let's put your knowledge to the test with some practice problems. Count the frequency of each character in a string. Map roll numbers to student names. Count the number of distinct integers in a vector. Store and update the last seen index of elements in an array. These problems will give you hands-on experience with insertion, lookup, and traversal of maps. It's quiz time. Let's see how much you have picked up. What's the difference between using m key and m.add key? Can you map contain duplicate keys? What the average time complexity of an unordered map operation? When does an unordered map equate to n complexity? These are key questions to assess both your conceptual clarity and practical readiness. To summarize, use map when sorted order of keys matters. Use unordered map when performance is the priority and order does not matter. Understand how to access key value pairs via dot first and dot second. And always be cautious of inserting values silently. It can lead to hard to find bugs. Maps are a core part of STL and mastering them opens doors to writing clean, efficient code in C++. Great job, see you in the next session. Hello and welcome back to our in-depth journey through the STL. This is day 18 and today we are focusing on a container that often files under the radar but is incredibly useful in the right situations. It is the multi-map. We will look at how it works, when to use it, how it compares to similar containers like map and unordered map, and explore some practical real-world applications. So if you have ever wondered how to handle duplicate keys in STL, this is the session for you. Let's begin by understanding what a multi-map actually is. At its core, a multi-map is an associative container, which means it stores elements in the form of key value pairs just like a map. But here's the big difference. Unlike map, which only allows unique keys, a multi-map can store multiple elements with the same key. This makes it ideal when a one-to-one or one-to-many relationship exists in your data model. For example, think of a dictionary where one word has multiple definitions or a student receiving multiple grades. It's included in the map header, and just like map, it keeps its elements sorted by key. Internally, it's powered by a red-black tree which ensures the insertions, deletions, and lookups happen in logarithmic time. So it's both elegant and efficient. Let's now look at the syntax. Declaring a multimap is as simple as including the map header and using the multimap keyword. Here we have defined a multimap where each key is a string representing a student's name and each value is an int representing their score. Take note of these insertions. We insert Alice with a score of 90, Bob with 85 and Alice again with 95. This is perfectly valid in multimap. It does not overwrite the earlier Alice entry like a map would. Instead, it keeps both, and the container ensures that keys are kept in sorted order, so Alice entries will appear before Bob in this case. When it comes to inserting elements into a multimap, we have several flexible options. First, we can use the insert function with a pair to take advantage of C++11's initializer list syntax, like we saw earlier. If you have a range of elements, say from another container, you can use range insertion mmp.insert start, end. A key highlight: since multimaps allow duplicate keys, every insertion is preserved. Unlike map, where adding a key that already exists would silently fail or overwrite the value, multimap welcomes duplicates. This makes it reliable for collecting grouped data. Now let's talk about how to access data in a multimap. This is where things differ significantly from a map. A map allows you to use the square operator for quick access like key, but a multimap does not support this because square brackets assumes a one-to-one mapping of key to value. With multimaps, we might have multiple values per key, so it requires a different approach. Instead, we use member functions like find key to get an iterator to the first matching key, lower bound and upper bound to define ranges, and most importantly, equal range. This gives us a pair of iterators representing the full range of values associated with a given key. In the code shown, we retrieve all scores for Alice using equal range, then loop through that range and print each score. This pattern is incredibly useful when handling grouped data. Just as important as inserting and accessing data is knowing how to erase it. With a multimap, there are three main ways to remove elements. First, we can pass a key to erase to remove all elements that match that key. Second, you can erase an element by passing a specific iterator, perfect when you want to surgically remove just one occurrence. Third, we can erase a range of elements using two iterators. This fine-grained control is powerful, especially in applications where data is dynamic and changes frequently. So when should you actually use a multimap in your applications? Here are a few real-world scenarios. Student grades. A student might have multiple scores over time. You want to group them by name but keep all scores. Word context mapping. Suppose you are building a text analyzer tool and you want to map each word to all the positions it appears in a document. That's a natural fit for a multimap. Event scheduling. If you are building a calendar or scheduler, you might have multiple events occurring on the same day. You need to associate that single key, the date, with multiple values, the events. These examples show the versatility of multimap when it comes to modeling real-world one-to-many relationships. Let's now compare multimap to its close cousins map and unordered map. First, duplicate keys. Only multimap allows them. Both map and unordered map enforce unique keys. Next, ordering. Map and multimap maintain sorted order of keys thanks to their underlying red-black tree structure. Unordered map, on the other hand, uses a hash table, so the elements are sorted. Elements are stored in an unpredictable order. In terms of access, only map and unordered map support a bracket operator. Since multimap can have many values per key, this syntax would not make sense. Finally, time complexity. For most operations like insert and lookup, map and multimap offer log n performance. Unordered map is generally faster with average case of constant time, but only when you don't care about ordering. This comparison is critical when choosing the right container for your problem. Alright, let's test what you have learned with a hands-on challenge. Your task is to write a program that shows and displays the scores of students. Remember, students can appear multiple times, so duplicate keys are expected. The input might look like this: Alice 90, Bob 85, Alice 95, and Bob 87. The output should group scores by student. So for Alice, you would print 90 and 95. Use equal range to retrieve all the values for each student. This is a perfect real-world use case where multimap shines, grouping data efficiently and keeping it stored. Let's wrap up today's lesson with the key takeaways. Multimap is an STL container that allows multiple values for the same key. Unlike map, it does not support the bracket access operator, so we rely on find, equal range, and related methods. Internally, it maintains sorted order, just like map, making it useful for ordered traversals. Whenever your data follows a many-to-one relationship, like multiple grades per student or multiple events per date, multimap should be your go-to choice. Choosing the right container not only makes your code more efficient, but also more intuitive to read and maintain. And that brings us to the end of today's session on multimap. I hope you now see the power and flexibility that this container offers, especially when dealing with duplicate keys. If you have any questions or want to explore deeper use cases, feel free to ask. In the next session, we will look at how to customize sorting behavior using custom comparators in sets and maps, a feature that gives us even greater control over your data structure. So I will see you there. Hello and welcome to day 19 of our STL Mastery series. Today we are diving into an advanced but essential concept in C++ STL, custom comparators in sets and maps. This lesson will unlock a powerful layer of control over your containers and elevate your understanding of how data can be stored, accessed, and sorted efficiently and intuitively. So let's begin. Here's what you will take away from today's session. First, you will understand why default sorting isn't always enough and when custom comparators become necessary. Next, you will learn how to implement custom comparators using three primary approaches: functors, lambda functions, and operator overloading. And finally, we will see how these techniques are used in real-world applications like ranked lists, task schedulers, and leaderboards. By default, ordered containers like set and map use std::less, which sorts elements in ascending order. But what if you want descending order, or need to sort a complex object like a student by marks and then name, or organize employees by salary? These cases can't be handled with default behavior. That's when you define a custom comparator, giving you precise control over how elements are compared and stored. This is especially important in real-time systems, dashboards, and algorithm challenges. Let's start simple. The greater comparator is built into the STL and reverses the default sort order. In this example, we use set int greater int and the numbers are stored in descending order from largest to smallest. It's a handy shortcut when all you need is reverse sorting and you don't want to write custom code. Now let's go deeper. A functor is a class or struct that overloads the function called operator. In this example, the test functor compares two integers and returns true if the first is greater than the second, achieving descending order. Functors give you flexibility. You can keep internal state, reuse the logic, and even template them for multiple types. Functors are especially useful when dealing with user-defined types. Take this student struct. It contains an ID and a name. the default comparison won't know what to do with it. By creating a compare by ID functor, we define custom logic to sort students in their ID. Without this, the set would not know how to insert or arrange the students at all. Sometimes you don't need a full functor, you just need a quick comparison for a one-time use. Lambdas are perfect for this. Here we define a lambda that compares two pairs by their second value. Using take type and passing the lambda into a set, we achieve custom ordering inline. It's elegant, functional, and keeps code concise, especially for sorting collections of pairs or tuples. There are a few things to keep in mind when writing custom comparators. First, your comparison must follow strict weak ordering. This means it must be consistent and logical. Otherwise, the container's behavior becomes undefined. Second, remember that in maps only the keys are compared, not the values. Also, unordered containers like unordered map or unordered set don't use comparators, they rely on hash functions. Lastly, if your object already overloads, you may not even need a custom comparator. Here's a realistic and very common use case. Sorting students first by their marks in descending order, and if the marks are equal, then alphabetically by their names. To achieve this, we define a student struct and a comparator that first checks marks and only checks names if marks are tied. This compound logic is a classic pattern, and you will encounter it frequently in ranking systems, data dashboards, and competitive programming problems. Now let's put your knowledge to the test with a few mini tasks. Try creating a set that stores integers in descending order. Then define a map that uses a custom object as the key, stored by a specific property like name. Next, write a lambda comparator to sort a set of pairs. And finally, write a compound comparator that sorts based on two fields like we saw in the last slide. These mini challenges will help reinforce your understanding. Custom comparators often show up in interviews. One common question is, how do you sort a map by value instead of key? This isn't directly supported, so you would extract the contents and sort them manually. Another question, how do you sort a set of structs? Here you would use custom comparator, just like we did with students. Finally, many candidates get tripped by unordered containers. Remember, they don't support custom comparators because they use hashing instead. To stretch your skills, here are some practice problems. Build a system that stores employees sorted by salary with a fallback sort on each, or create a live leaderboard where participants are ranked by scores and names. You could also design a data structure that automatically maintains the top n items using a custom rule. Each of these problems will challenge your comparator logic and sharpen your STL fluency. Here's a quick summary of what we have covered today. We explored the built-in creator comparator. We wrote functor-based comparators to sort integers and structs. We used lambda expressions to simplify custom logic inline. We handled stark comparisons and applied these concepts in real-world scenarios. Each of these tools gives us tighter control over our data structure. Before we wrap up, here's your homework for today. First, design a leaderboard using set or map, sorted by score in descending order and name in case of ties. Second, create a task manager where tasks are sorted by priority from high to low and for equal priority by earliest deadline. These tasks mimic real-world problems and will solidify your mastery of custom comparators. Welcome to day 20 of our STL course. Today we embark on a key topic in the STL ecosystem, iterators. These are the foundation of container traversal and a gateway to using STL algorithms effectively. In this session, we will dive into what iterators are, explore their different types like reverse iterators and const iterators, and even write a basic custom iterator. By the end of this lesson, you will not only understand how to navigate STL containers in multiple directions, but also how to do so safely and efficiently using iterator best practices. Let's get started. Let's take a look at today's learning objectives. By the end of this session, you will clearly understand what iterators are and why they are used in STL. You will learn how to use reverse and const iterators to handle different traversal scenarios. You will categorize iterators into types like forward, bidirectional, and random access. And finally, you will understand how to create a simple custom iterator, an essential skill for designing iterable classes. We will also discuss common pitfalls to avoid while using iterators, so you can write safer and cleaner C++ code. So what exactly is an iterator? In simple terms, an iterator is a generalized pointer. It acts like a pointer in that you can move it forward or backward and dereference it to access elements. But unlike raw pointers, iterators are safe type and container aware, meaning they know how to work with STL containers. They provide a common interface that allows us to traverse elements without knowing the container's internal structure. Thanks to iterators, algorithms like sort, find, accumulate, and many more can work with any container uniformly, whether it's a vector, set, or map. They truly embody the power of abstraction in STL. STL classifies iterator into 5 categories, each offering different capabilities. Let's go and explore them. Input iterators. These can read data as we move forward through a container. You can think of them like reading from a file or stream. Output iterators. These are used to write data, for instance writing to an output stream or inserting into a container. Forward iterators. These support multiple passes in the forward direction, useful in singly linked lists. Bidirectional iterators. These can move both forward and backward. Think of list and set. They support bidirectional iteration. Random access iterators, the most powerful. They support direct jumping, like moving ahead by 3 positions instantly. Containers like vector and DQ support this. Understanding which type your container supports helps you choose the right algorithm and method for the job. Now let's explore constant iterators or const iterators. These iterators offer read-only access to the elements of a container. You can traverse using them, but you cannot modify the values they point to. This immutability is valuable in several scenarios. When working with functions that must not alter other container, when you want to guarantee safety in large collaborative code bases. In code, we use cbegin and cend instead of begin and end to get const iterators. This ensures your code won't compile if someone tries to modify an element within the loop. Const iterators enforce discipline. Sometimes we want to iterate in reverse order, from the end of a container to the beginning. STL offers a neat solution, reverse iterators. To use them, we call rbegin and rend on a container. For constant access, we use crbegin and crend. For instance, you can see this code. This prints the vector from the last element to the first. Reverse iterators come in handy in sorting, backtracking algorithms, or whenever the last elements have higher priority, like when implementing undo features or history stacks. It's time to look at an example that uses all 3 major iterator types: the regular, constant, and reverse. In this code snippet, the regular iterator iterates and updates the vector elements. The constant iterator ensures read-only access. The reverse iterator prints the modified values in reverse. By mixing and matching these iterator types based on your requirements, you gain both flexibility and safety in your code. Now it's time to take a step further into custom iterators. Why do we need them? Imagine you are creating a new data structure like a graph or matrix. To make it compatible with STL algorithms like for each or sort, your class needs to expose an iterator interface. Custom iterators provide that interface. They allow you to define how your object should be traversed. It's a powerful tool that elevates your C++ skills, especially if you ever work with non-STL data structures or build your own. Here's a simple example of a custom iterator embedded inside a class. We have a myContainer class with a nested iterator class. This iterator overloads key operators like not equal to, plus plus, and STL multiplied, allowing us to use it in a range-based for loop. We define begin and end to return instances of our custom iterator. This way our class becomes iterable, just like STL containers. This is a basic version, but it captures the core idea. In production, you would add bounds checking and possibly support for reverse iteration too. Let's go over a few common mistakes when working with iterators so you know what to avoid. Modifying with const iterator. You will get a compile error if you try changing elements. Use regular iterators when updates are required. Incorrect use of AND in reverse iteration. If you use AND instead of RN in reverse loops, the logic breaks. Dereferencing invalid iterators. This happens when you access an element after releasing it or from an empty container. Always validate your iterators. Avoiding these pitfalls will save you from undefined behavior and confusing paths. To reinforce your understanding, try out these problems. Reverse print a vector using both for loops and reverse iterators. Create a matrix wrapper class and implement a custom row-wise iterator. Use reverse iterators with a map to print key value pairs in descending key order. Compare regular versus constant iterator usage and performance. These exercises will help you apply today's concepts and build deeper familiarity with iterator mechanics. Here's a fun mini challenge. Write a function called print backwards that takes a dequeue of strings and prints each element in reverse using a reverse iterator. This exercise checks your understanding of both containers and reverse traversal. Try implementing it after this lesson. It's a short but insightful. Let's wrap up. Today we have learned what iterators are and how they abstract traversal in STL, how to use constant iterators for safety and reverse iterators for backward traversal, the 5 categories of iterators based on their power, and how to write a basic custom iterator to make your classes STL compatible. You also reviewed pitfalls and practiced real problems. With iterators in your toolkit, you are now ready to work more efficiently with STL containers and algorithms. Great job today! Welcome everyone to day 21 of our STL journey. This marks a major milestone. You have completed 3 full weeks, covering containers, iterators, and associative structures in depth. Today's session is a special one. It's focused on applying everything you have learned so far. We will begin with a rigorous practice set that targets real-world STL usage. Then we will dive into a comprehensive mid-course quiz to evaluate your understanding and highlight areas for improvement. Let's dig in. Here's our roadmap for the day. First, we will spend around 3.5 hours working through STL-based practice problems. These problems are carefully designed to span across the different containers and concepts we have covered. Then comes the 90-minute mid-course quiz. This will assess both your conceptual clarity and your ability to write STL-rich code. After that, we will go into a review and feedback session, where we will discuss the trickier problems, explore different solution approaches, and reflect on your performance. Finally, we will look forward to week 4, where we begin exploring the incredible power of STL algorithms. Let's get clear on the objectives for our practice session. First, we want you to strengthen your foundation in using STL containers. You have seen how to declare and manipulate vectors, dequeues, maps, and more. Now it's time to apply that knowledge. Second, we want to help you build confidence through problems that mimic real programming scenarios, whether it's system design or competitive coding. Lastly, today's problems will challenge you to apply custom iterators and comparators, concepts that are essential when moving beyond textbook use and into real-world STL usage. By the end, you will not just understand STL, you will be using it like a pro. Let's quickly revisit the STL containers that are in focus for today's practice problems. First, vectors. You will use vectors to manage dynamic data like student records or sorted lists. We will focus on operations like pushback, insert, erase, and resize, and we will play around with nested vectors and sorting pairs. Then comes a DQ or doubly ended queue. You will use this in problems that require efficient insertion and deletion from both ends. Think of problems like sliding window maximum or browser history simulation. The list, a doubly linked list implementation, will be used in safe insert delete operations where maintaining iterators is critical. With stacks and queues, we will implement classic concepts like expression evaluation, valid parenthesis check, and job scheduling queues. This will build your LIFO and FIFO logic muscles. Moving to the second set of containers, these are slightly more advanced. The priority queue will be used for problems that require frequent access to the highest or lowest elements. You will implement top k frequency problems and work with custom or comparators to control ordering. With sets and multisets, we will look at how to remove duplicates, perform range queries, and track counts of repeated elements. Then we move to maps and multimaps. You will build frequency tables, groupings, and record trackers. This will be helpful in problems involving word counts, student marks, or inventory systems. Finally, we will experiment with iterators, especially rewards and const ones. You will also write your own functors and comparators to sort elements based on custom logic. Altogether, these containers and concepts form the backbone of modern C++ problem solving. Let's walk through some of the practice problems you will be working on today. Problem 1 involves using a vector of pairs to store student names and marks, then sort them by marks in descending order. In problem 2, you will implement a sliding window maximum algorithm using a DQ. This is a classic real-world pattern seen in stock analysis or real-time monitoring systems. Problem 3 is a browser history simulator using a list, allowing you to go forward and backward while preserving your iterator positions. Problem 4 requires you to design a min stack. You will use two stacks to track the minimum element at every stage. In problem 5, you will combine maps and priority queues to find the top 3 most frequent elements in a list. And in problem 6, you will use a set with a custom comparator to store and sort employee records based on joining date or salary. These problems offer a powerful blend of logic, design, and STL fluency. Here's how the practice assignment is structured. You will receive a PDF problem set with detailed instructions. Each question comes with an input format, output specification, and examples to test your logic. You are encouraged to solve this using either a local C++ IDE like Visual Studio Code or on competitive platforms like HackerRank or LeetCode for a timed environment. Remember to focus on code readability, proper use of STL functions, and logarithmic efficiency. Finally, discuss your approaches with your peers. If you are working in a group or classroom, collaborating on edge cases and optimizations will help deepen your understanding. Now let's talk about the mid-course quiz. This is a 90-minute assessment worth 60 marks. It's designed to test everything from syntax and logic to real-world STL application. The quiz covers material from days 1 through 20, including vectors, stacks, sets, maps, iterators, and more. We are using a mixed format structure to give you a well-rounded challenge. Let's look at the breakdown next. Here's how the quiz is structured. First, you will face 10 multiple choice questions designed to test your conceptual clarity, things like time complexity, container properties, and STL functions. Next, there are 5 output prediction problems. You will be given small STL code snippets and asked to find the output. Then come 5 syntax filled questions and where you will complete a code segment by choosing the correct STL code. After that, you will solve 2 short coding questions where you will write STL heavy code for a small task. Finally, there are 2 scenario-based problems. You will be given a real-world use case and asked to choose the most optimal STL structure to implement it. This quiz is a true STL skill set. It pushes your syntax, logic, and design thinking. Here are a few sample quiz questions to give you a feel. MCQ, which STL container offers constant time insertion at both ends but not in the middle. Output prediction. What what's the output of a vector after calling insert v dot begin plus 2 comma 5 on a vector of size 4? Syntax fill. Fill in the blanks to erase all elements greater than 10 from a multiset. Coding task. Write a function that returns the top 3 frequent elements using a map and priority queue. Scenario. You are building a undo redo system. Which STL container would you choose and why? These questions are as close to real world thinking as possible. Let's reflect on what you will walk away with today. You will have practical experience with STL through diverse problem solving. You will see firsthand how STL saves time, simplifies logic, and makes your code robust. You will also gain feedback on your performance, which STL concepts you have mastered, and which areas need further attention. More than that, you will experience the joy of solving real problems, problems that mimic challenges faced in product development, software interviews, and competitive contests. Today is about leveling up, not just in knowledge, but in confidence. That brings us to the end of today's session. We will now have a quick wrap up discussion, highlighting creative solutions, common mistakes, and how to optimize further. Then we will look at your quiz results, compare scores anonymously, and talk about strategies for improvement. And as we step into week 4, get excited. We will dive into the power of STL algorithms. Functions like sort, countif, partition, and accumulate are about to transform how you solve problems. You have done great so far. Let's keep the momentum going.